Think of a chemical bond like a piece of sturdy rope connecting two weights. If you want to separate those weights, you could untie the knots, or you could simply take a pair of scissors and snip the rope right down the middle. In the world of organic chemistry, most reactions are like untying knots, carefully swapping one atom for another. But ozonolysis? Ozonolysis is the pair of scissors. Let's look at a standard carbon-carbon double bond, the alkene. It's the backbone of countless organic molecules. Usually, these double bonds are quite resilient, but oxygen has a more aggressive cousin, ozone. While the oxygen we breathe is O2, ozone is O3, a strained, energetic molecule that is itching to fall apart. Watch what happens when we introduce ozone to our alkene. As the ozone molecule approaches, notice how it doesn't just attack one side. It wraps itself around the double bond like a bridge. This creates a fragile, ring-shaped intermediate called a malosonide. But this structure is incredibly unstable. In a frantic molecular dance, it literally turns itself inside out, rearranging into what we call an ozonide. At this point, the original carbon-carbon bond, the very spine of our molecule, is gone. It has been completely severed. But we aren't finished yet. To get our final products, we need to work up the reaction. Imagine we add a little bit of zinc and acetic acid. This acts as a pair of molecular hands that reach in and grab that final lingering oxygen atom from the ozone ring. As that bridge collapses, the carbons are forced to stabilize themselves by forming new double bonds with the remaining oxygen atoms. And here is the aha moment. Look at the result. Where we once had a single long chain with a double bond in the middle, we now have two separate pieces. The double bond has been replaced by two carbonyl groups, specifically aldehydes or ketones. But why do chemists love this reaction so much? It's because it's the ultimate diagnostic tool. Picture a complex mystery molecule with a double bond hidden somewhere in its long chain. It's hard to tell exactly where that bond is just by looking at the hole. But if we perform ozonolysis, we cut the molecule at that exact spot. By identifying the two smaller pieces that fall off, we can work backward, like a detective at a crime scene, to piece together exactly where the original bond must have been. Ozonolysis reminds us that in chemistry, sometimes the most constructive thing you can do is break something apart. By destroying the bond, we finally reveal the true architecture of the molecule.